Hello and welcome to another C++ video here on my channel, and today we're going to be talking about smart pointers in C++. So I basically just want to demystify pointers and give you some advice on which kinds of pointers you should be using and when you should be using. So let's begin with what are pointers. So one of the best pieces of advice that I try to get in people's head is that everything, quite literally everything, inside a computer is data, right? And this applies to your programs as well. So the compile code of your program is just data. A website coming across the internet into your browser, the music you listen to on Spotify, it's all just data coming across the wire, right? So you might be wondering where is all of this data stored at the runtime of your program? So for the sake of simplicity, when the data that you acquire for a program, such as your variable data, that data is usually stored in your machine's RAM. So in essence, every variable, every array that you create, every piece of information you're creating and storing with your program has a location in your computer's memory. And this is what pointers really are, is the location of where that piece of data is stored at the runtime of your program. In other words, the byte offset of that particular variable in your program's virtual memory. In C++, you can create a pointer using the star operator, right? So let's actually do some code here so I can explain a little bit better. So say we had a little struct called myStruct here, right? And we had some integer data here, right? So it doesn't matter what it is, as long as you have some data in your structure, this will kind of work in the same way, right? So yes, you can absolutely create an instance of myStruct here by just doing something like this. And you can pass in an integer here, which will be the value of this data type here. And this is going to be stored in the stack of my function here, in this case, the stack of my main function. But you can also create an instance of this structure as a pointer, so as a value in something that we call the heap, or in the free store, depending on how you've learned it. So the heap is not quite the stack, so the data is actually stored a little bit farther away from where you call it, basically. And the heap is basically the place where your operating system can dynamically request and free memory, right? So to create this in the heap as a pointer, you do something like this. Now, this is basically how you create a pointer in C++, right? So the value of my instance here isn't actually referring to the struct itself, but instead it stores an integer value such as 0x, FFF, or whatever it is. And this number simply means the address offset where the data for the struct starts, right? So usually this pointer value is a 64-bit number in 64-bit machines, 32-bit number in 32-bit machines, and so on. And if you've actually played with pointers in C++ before, you know that you can basically print out the value of the pointer, something like this here, right? And you will see some output like what you can see here on the bottom. I'm not sure if it's visible. It is. And basically this is what a pointer stores. A pointer variable is just an integer, which is the offset for that data in your RAM. Now to use the pointer, we must first dereference it in the program, right? So this is done in C++ again with the star operator, the prefix star operator, and you can do something like this, right? So you can do this, and then let's just open that, my instance dot data, like you can see here. And you can do a stud and line for the sake of simplicity. I'm going to remove the previous pointer value here, and we actually get to see the data value in here. Now in C and C++, there's also a better way of doing this exact same thing here with the syntax sugar of the arrow. So you may have seen code like this one. So this .data, and this is essentially the same thing as what we had before. It just does the reference and the access to data at the same time here, right? Now this tells the compiler to pretty much trust that the data in the offset stored by this pointer value here is of my struct type, right? And this mostly works if you do actually have a valid structure stored in the given pointer there. But if you don't, well, then your program might crash with some random values being read as they're valid, because the program is going to try to interpret whatever blob of data is in that offset as my struct. So this is a big problem with pointers, and it's cause of a lot of crashes basically. Now another common issue is no pointer dereference, which most of you might already know about. What happens is that C, C++, and other languages use the value 0 to represent a null, invalid, or a no pointer. And dereferencing a pointer variable that is null results in a runtime crash, right? This is probably the most common type of pointer related crashes, and also many different exploits around the world. And the most simplest way to actually get a no pointer in your program is just to basically declare it and not define it here. So this will by default be initialized as a no pointer here, and you will indeed get a sig term here, so your program will crash and it will be a no pointer dereference here. Now you can have no pointers by using just no pointer in C++ as well. That's probably the most common way of explicitly declaring a pointer as no pointer at the start. So this is also a bad thing here. So if you're creating pointers, you should always make sure that you initialize them to values that are correct, either by creating the pointer yourself in the heap, so something like this, so my struct as we had it before, 10, or by getting that pointer from an already created instance, such as this one here. You can also do this in C++. So my other instance here, and just put the value of 10 here, for example, and you can do something like this as well. This will get the value of the pointer of this stack variable here. This is also valid code in C++. And it's very useful when you actually have functions that take pointers, but you only have sort of like stack variables. You can just get the pointer for that stack variable. When you're done using the pointer data, you must delete that data. And this is something that C++ doesn't do for you automatically. With stack variables, so when you create just a normal variable, that data will get deleted at the end of the function or at the end of the class lifetime or wherever it is. But with pointers, you need to do it, which means that this program here actually leaks data. You can see that we create an instance, but we never delete it. So this is also bad. So you should always call delete on my instance down here. And this is a well-formed program now, shall we say. Now, the delete keyword will invoke the free function internally, which in turn invokes OS-specific functionality to free up that memory in your machine, right? So it's worth knowing that as well. So essentially, we have three fundamental problems with pointers. The first one is the first one we mentioned, which is interpreting invalid data as something that's valid and potentially crashing your program. We also have no pointer dereference, which is mostly caused by uninitialized pointers. And third one is the pointer data lifetime. So when you should be deleting the data, because you have to keep track of it. And everything we've seen here so far has been about raw pointers. So the oldest way of creating pointers in C++. We will get to smart pointers in a second, but first I want to talk a little bit about references, because I feel like references are also worth talking about when you're talking about pointers, because they kind of solve the same problem of indirection and basically avoiding popping things when you're sending them to functions, right? So in C++, references exist. You might be aware of that. So for example, you can have here a function that will take a reference to a my struct, right? And say that this function simply just printed out the value of the data, right? So data.data, that's it. Now you can see here this funny little symbol here, the ampersand. This just signifies a reference in C++, which means that the data is being taken by a reference and is not being copied into the stack. In other terms, passing the pointer in a nicer syntactical way to this function. Now I understand that the C++ ISO says that references are not pointers, but compile code using pointers versus references is usually identical. So under the hood, they behave in the same way. And thinking of references as easier and better to use pointers is more beneficial to C++ programmers, especially the beginner ones, right? So references are pretty much just pointers as well in C++, but with much better usability semantics here. So in this case here, you can see that we just use the reference as it's a variable, right? So it's just a binding to a variable. We don't have to do any sort of like dereference shenanigans, any sort of like arrow operators here to access the data. It's just a variable from your point of view. And you can create variables that are references in C++ just as well. So you can do something like this. My struct reference is my instance ref here. But the crucial part of references is that C++ will not let you leave a reference undefined, right? So you must define a reference when you create it, which avoids the same problem that pointers have, where you may have a no pointer when you create it, right? So if you forget to actually assign the pointer a actual pointer value, that doesn't happen with references. So you must actually put something in here. So in this case here, yes, we could use, a reference to that pointer. So you can do a my instance here, and then you can call that function that we had. So print data, print data, and this will also print out the value. Almost commonly used, you just basically have a my struct here, which is my actual or my stack instance with 10, and you either create another reference here, which I don't see why you need it in this case, but you can just you can bind this struct to my stack instance, which will compile. Or even better here, if you just have a stack variable, you can just pass that stack variable in here and it will automatically be converted to a reference in C++. This just happens, which is probably the way people use references the most, right? And they should have actually been my stack instance. But what I'm trying to get here is that because references must be initialized, you can't leave a reference uninitialized and then use it later. So my instance ref here, You just can't do that in C++, which means that they will hold a valid reference to a variable here. So if you leave it uninitialized, you can see that the compiler is actually shouting omit because we don't have an initialized reference here. So this is what references are. They're just pointers under the hood with better use semantics, and you can't actually have a no reference. However, it is still possible to have invalid references in C++. So for example, you can initialize a reference variable to an invalid pointer. The simplest way to do this is just to, have a null pointer here and then basically just initialize that instance to something like, like this in here. And, this will compile, but your code is still wrong and it will still crash because you essentially here have a null pointer dereference, just sort of like masqueraded as a reference instead of a pointer here. But, it's still possible to get references wrong. Especially when you look at lifetime issues where you may have a reference to a valid variable, but that variable essentially just gets deleted, before you've actually used that reference. And when it comes to using it, you're using data that's no longer there, right? So these things are still possible with references. So the question is, when should you use references instead of pointers, right? So for me, I generally use references in the APIs of functions such as this one here, whenever I want to avoid very expensive copies. So if I have a very, very large vector that I'm passing into a function, I will pass that as a const reference, and that's actually done like this here. So your data will not be copied. You're basically passing the pointer to that data. So, that data is still in the same place. You haven't copied it anywhere, and your program is going to be a little bit more efficient because of that. I completely avoid any type of pointers as much as I can. So keep that in mind. And now let's move on to smart pointers. Now, smart pointers. So the C++ standard has recently, well, not actually that recently, introduced pointer containers to the standard. So those are actually available in the memory header. You have to include the memory header up here. And these types are, stud unique pointer like this, and stud shared pointer, and also stud weak pointer, I believe it is. So these three types of pointers serve different purposes, and we'll talk about each one individually. But these should be your preferred way of using pointers if you have to use pointers in the first place. And these three pointers are essentially just wrappers around raw pointers, or shall we say the dumber raw pointers. And this wrapping functionality differs in interesting ways between the types, right? So unique pointer, shared pointer, and weak pointer have different purposes, as I said. Now, the benefits of using smart pointers is that you don't need to keep track of the lifetime of the pointers yourself. In other words, you don't have to delete the pointers or the smart pointers because the language is keeping track of the usage for you, right? And the way it keeps track differs, as I said. We'll look at each one individually. What I want you to get out of this video is that each of these smart pointer types is intended to be used based on the, shall we say, the ownership of the pointer data in your program, right? So let's begin with unique pointer. So unique pointer is perhaps the simplest smart pointer abstraction in the standard. Now, I believe it's called unique pointer because the underlying data here is only owned in one place, right? So it's either owned by the function you create the unique pointer at, or that struct or class that holds the unique pointer member. But what does this actually mean? So does it mean that you can only use unique pointers where you create it, i.e., inside the function or class that owns it? Well, not quite. It just means that wherever the lifetime of the function or the object that owns that unique pointer finishes, then the pointer data will automatically be deleted as well. So let's actually make this example a little bit more interesting by adding constructors and destructors here so you can see what's going on, right? So if I had a myStruct constructor, which takes an int for value, and that just did data equals data here, right? And we also had a destructor that just prints out that it's been destructed. And let's add the print here, shall we? And we had a destructor as well. Now, in the very basic example that we had at the start, where we just had a pointer here, right? So something like new myStruct, and we're passing the value of 10 here. And we removed this delete function here. You can see, well, at the moment here, because we had the delete there, you can see that the destructor got called. But if we didn't have it, then the destructor would never be called, right? So you'll be able to see that in here. Now, if instead we were to use a unique pointer in this case, so if this was instead something like this, and this is perhaps the most simple way you can create unique pointers, you can see that the object was constructed here. The constructor is mentioned in here. And at the end of my function, it was automatically deleted for me. I didn't have to do anything there, right? So this is one way of doing it. So you can create unique pointers like this, or you can also do something like stud make unique, which is probably my preferred way of doing it. Now this has the same effect, it just creates a unique pointer. Try and use make unique whenever you can. But the point is, this unique pointer instance here, I don't have to worry about the lifetime. Like I just create it here, I can use it in the exact same way as a pointer, and at the end of my function, at the end of the lifetime of the pointer, things will just be deleted as they have to. So let's get to a more interesting part of unique pointers. So what makes unique pointers unique? Well, the unique part of the name just means one thing, right? So copy constructors and copy assignment operators are deleted. You can't use them. So what does that mean in practice? That means that if I had, this unique pointer, as you can see up here, and I would like to actually have a copy of that. So I want to say I want to, have the same pointer in two different variables, like this one here. My other instance equals to my instance. This will not work. This will not work just because we are trying to copy this pointer into my other instance, which is a deleted function, as you can see here on the logs. C++ will not let you do that. So a very logical question would be, how do you pass this pointer into a function? So let's say this print data here actually took a unique pointer of my struct. So how do you actually call my data? Because you can't simply do something like this, print data, and pass in that pointer to it. So my instance here. This doesn't work. This will not compile because, as I said, you can't copy the pointer around. Well, the simple answer for this case here is just to actually take a reference to the pointer. You can't, pass a reference to that pointer because then the pointer is not being copied and you are still referring to the same pointer data. And obviously you should probably try and const it as much as you can as well for, good practices. But another logical question would also be, what if I don't want my main function to own this pointer anymore? What if I actually wanted my print data to own that pointer and delete it? You can, in unique pointers, move them. And moving is a different concept to copying. So moving, you're essentially not copying the data, you're just moving the pointer ownership to a different unique pointer. And you can do something like this here. So you can do move my pointer, I believe it is, and this will compile. However, it's not a well-formed program, and I'll explain why in a second. But you basically, by doing a std move here, you've given away the ownership of that my struct data to this pointer inside this function here, and that's what it does. Which now means that from now on, in the main function, you cannot use my instance anymore, because this is no longer a valid unique pointer. You no longer have a valid pointer, and you will crash your program if you try to use that. And this is the bread and butter of working with unique pointers. It's a very simple model here. I just took a little bit more time explaining it because I feel like all C++ developers should know the differences between a raw pointer and a unique pointer very well. And here it is. This is what a unique pointer does. So a shared pointer is basically the opposite of a unique pointer, right? In the sense that it's a pointer that can be owned by many different actors. So you can have many references of it. In other words, you can copy the pointer around. So the data of a shared pointer is only deleted when all the copies of a shared pointer are destroyed and no one is looking at it anymore, shall we say looking with quotation marks here. And the language keeps track of the references by maintaining an internal atomic counter which increases or decreases every time a shared pointer is copied or deleted, right? So every time it goes out of scope, it's deleted. Every time you create a new copy, that counter increases. So shared pointers are useful when you have a piece of data that need to kind of live as long as there's someone referring to it, and that's basically the usage of it. And an example of that might be you have a config structure where you may load some data for your program. And that config structure is basically stored in one place. It's in the heap, but you want to reference it in many different places. So you probably use a shared pointer for that. But that's essentially what a shared pointer is. So, if we were to convert this code to use a shared pointer, we would do something like this, right? So you want to move all of these types of shared pointer. And then instead of make unique, you have make shared, just like that. Make shared. There. And you no longer have to actually have that move anymore because you can in fact copy shared pointers. It's just the way that they are. But do bear in mind that shared pointers, because they have that extra sort of like reference counting functionality, there is a little bit of overhead compared to unique pointers. They will probably make your code slower if it's been used, all across your very sort of tight loops that you have in your program, right? If I'm honest, once you understand unique pointers, once you know kind of what the ownership model for that one is, Shared pointers is kind of the opposite of it. It can be owned by many people, and that's done with reference counting. So I'm not going to take too much time in explaining that. The syntax is almost the same as unique pointer. Just, go and use it, get some practice on it. So let's move on to weak pointer. So to keep it simple, weak pointers are basically shared pointers that don't increase the reference count. They don't actually own the data. And we use this type of pointer mainly to break circular dependencies. So you may have, for example, two different structures where one structure has a shared pointer to a struct B, shall we call it? But struct B has a shared pointer to struct A. Now, this is a problem because you have a circular dependency there. And if they both hold a shared pointer to each other, the data will never be deleted because the reference count will never be 0. Because whenever those two go out of scope, the other one is holding a reference to it. So that's basically it. And there's this very good article by this person, I hope I pronounced the name correctly here, Sorush, which explains the problem in detail. I'm going to leave a link in the description. I don't think it's very productive for me to actually try and code the same thing here, but you can see the problem here. So like they have a struct called team, which kind of holds a shared pointer to a goalkeeper, and a person struct, which holds a shared pointer to a team. And you can have, cases like this one where you have, the Barcelona team, which is a shared pointer to a team. And you also have Valdez, which is a shared pointer to a person. And you set the pointers to kind of point at each other, and they never get deleted in this case, right? And this is where the weak pointer comes in. So if you turn one of these pointers here, shall we say the person one to a weak pointer to a team, then person isn't actually going to own the pointer to the team, which means the reference counter never gets increased. It's just observing that data, which means you don't really have a circular dependency. Now, the drawback of weak pointers is that the usability is a little bit different, right? Because you don't actually own the data. You have to make sure that, whatever pointer you're looking at, whatever shared pointer it's basically kind of looking at, then it has to be valid. And you can do that with the .lock function. So whenever you have a weak pointer, you must call .lock and check that the pointer is actually valid for you to use it. Now, this is the difference between a weak pointer and a shared pointer. So a shared pointer has a reference counter, and it does increase that reference count whenever you copy it. Weak pointers don't do that, but you must call the lock function here. Now let's move to the advice for you. So how to use smart pointers. So how do I use smart pointers? Now, the general rule I use is the following. Don't use pointers unless you absolutely need them. And there are cases where you might need them. So for example, there may be algorithms that require pointer in direction. So for example, you may have like a difficult sort of like tree algorithm, which inherently requires you to have, pointers to the nodes and stuff. There are, as I said, structures that require pointers, and these are things like linked lists, for example, iterators as well. So those things are all kind of pointers under the hood, just nicer to use. There are design patterns like pimple, so pointer to implementation to hide the implementation of your software. So those do require pointers as well. And essentially, these are the circumstances where you may need pointers. But anything else, do not use pointers. Just stick to stack variables. Just stick to using C++ containers like vectors, strings, or whatever, and passing them around with references, because it's much nicer to use. It's much easier to actually reason about your code if you don't have pointers, going everywhere in your program. So I recommend doing that. Now, if you need to use pointers, here's the advice, right? So try and use unique pointers as a default. So this is by far the most restricting one, but also the simplest type, where you can quite easily reason about the lifetime of your object, right? So you know what happens to your object. You don't have to like see wherever it gets used to understand when it's going to be deleted, right? That's the thing. But if you need multiple owners, then use a shared pointer. But make sure that you actually need this, and you're not just like slapping a shared pointer on things just because you're not sure when an object should be deleted. That's what I can say here. Now, if you have shared pointers that reference each other, so if you have a possible circular dependency, then you should look at weak pointers, and you should make sure that you're using them right by kind of locking the object, making sure it's a valid pointer, and so on and so forth before you actually dereference it, right? So last but not least, use smart pointers whenever you can. So they are there to make your life easier in C++ with very little overhead. And just having the benefit of not having to worry about deleting a pointer is a major win in C++. There are so many bugs. I can't stress that enough. So many bugs with C++ and pointers just because people forgot to either delete them or properly initialize them. which, yeah, it can be kind of solved with if you're using smart pointers properly. Now, these points don't mean that you can't use raw pointers, right? It just means that you should think a little bit before you use them. So as I mentioned, there are cases where you need pointers, and a subset of those problems may actually require dumb raw pointers. So for example, I encourage you to go and try to write a doubly linked list in C++ with smart pointers, and you may find that you have a very hard time doing so. And you'll undoubtedly understand why sometimes raw pointers are fine from an implementation and performance point of view. It's just, some things are better implemented and easier to read with raw pointers. Now, I hope that you've enjoyed this video. Now, please let me know in the comments if you've ever struggled with C++ pointers, and if there's anything I can help with. I'm happy to get back to you as soon as possible. And please don't forget to like and subscribe to this video, and I appreciate your guys' support. I'll see you guys next time. Bye-bye.